Hypothalamus Artificial Intelligence, HI, presents to the companies in process of digital transformation, the short conference. State of the art of optimization. Algorithms, artificial brains, power computer and return on investment. HI supports its optimization know-how on its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. This video presents the research HI is conducting in this area. The growth of mathematical programming will not stop. The problems that can be solved every day, making use of computational power, will be greater every day, which for now will not stop. Just as the complexity of the problems grows, so will the mathematical intelligence of the human being, which has not stopped growing. Four aspects are fundamental in this growth. Artificial brains, new methodologies for thinking about optimization, computer power, permanent and accelerated growth in the calculation speed of computers, together with the power of communications. Algorithms, development of new algorithms in line with computational power, and return on investment, which stimulates the advanced artificial intelligence market. Artificial brains. This is the biggest challenge taken on by HI. It's the result of its 50 years of work in highly complex mathematical modeling. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. The artificial brains is the evolution of DSS under the Industry 4.0 revolution that is conceptualized as a set of mathematical models that exchange autonomously information between them, working online, using distributed optimization. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. This is how the human brain faces reality, using multiple models of reality, acting permanently in parallel, to make decisions. The algorithm that simulates the hypothalamus is assembled by Optex, the HI's cognitive robot, using the models that traditionally make up a decision support system. The artificial brains are the evolution of the multi-problem models that HI has been implementing since 1990. Today they are a disruptive methodology that may change the future of artificial intelligence. Computing power is critical in the development of optimization. The first machine designed to facilitate calculation operations has its origin in China about 2,500 years ago. It is the abacus. It is also in the Chinese I Ching or Book of Mutations where the first formulation of the binary system is found, 2000 B.C. In the West, the first historical references correspond to ancient Greece. We can find the first literary reference to an automaton of human appearance in Book 18 of Homer's Iliad. On the other hand, Thales of Miletus describes some aspects of static electricity. The word electron comes from his text. The Romans also used abacuses, with pebbles that they called stones, the origin of the current word. The construction of the first robot, which simulated a theater actor, was due to Heron of Alexandria, an expert in hydraulics. ENIAC stands for Electronic Numerical Integrator and Computer. It was the world's first general-purpose electronic digital computer, built between 1943 and 1945 for the U.S. Army to calculate ballistics trajectories during World War II. Designed by J. Presper Eckert and John Mauchly at the University of Pennsylvania, the ENIAC was a massive machine, weighing 30 tons and occupying a 1,500 square foot room, utilizing over 18,000 vacuum tubes. CDC, or Control Data Corporation, was a leading manufacturer of mainframes and supercomputers from the late 1950s to the 1980s, most famous for the Seymour Cray-designed CDC 6600, considered the first supercomputer. CDC's success was due to its innovative engineering and powerful machines, but financial difficulties and Cray's departure in the 1970s led to a decline, ultimately resulting in the company's exit from the computer market in the late 1980s. The IBM System/360, announced in 1964, was an innovative family of 64 bits compatible computers covering scientific and commercial applications, replacing IBM's previous incompatible product lines. The IBM System/370 is a range of computers, from entry-level to mainframes, announced in 1970 as successors to the System/360 family. Its innovative, scalable architecture and unified design, which established the 8-bit byte and a full 360-degree range of models, allowed for software compatibility across different machine sizes and set a new industry standard for computing. This innovation led to a highly successful and influential product line that continued to evolve into successors like the System/370 and Z series. The Cray-1 was a supercomputer designed by several computer scientists headed by Seymour Cray for Cray Research. The first Cray-1 system was installed at the Los Alamos National Laboratory in March 1976. It is one of the most well-known and successful supercomputers in history, and one of the most powerful in its time. As technical characteristics, the first version, Cray-1A, worked with vector processors at 80 MHz, was a 64-bit system and weighed 5.5 tons, including the Freon cooling system. Despite its large size, it only had 8 MB of RAM. The Cray-1A was the first supercomputer to successfully implement the vector processor design that improves the performance of mathematical operations by organizing memory and registers to quickly perform a single operation on a large dataset. We could say that the Cray-1A vector processor was the origin of the GPUs that NVIDIA and other tech companies produce today. With the advent of ENIAC, Dantzig created the simplex method, which gave rise to optimization algorithms. The systematic development of practical computing methods for linear programming, LP, began in 1952 at the RAND Corporation in Santa Monica, under the direction of George B. Dantzig. Dantzig worked intensively on this project there until the end of 1956, by which time great progress had been made on first-generation computers. Work continued at SARE Incorporated, in Washington for a few years and later in many places by many individuals and companies. By the late 1960s, elaborate program systems known as mathematical programming systems, MPS, had become a standard part of the optimization software available to various computers, notably IBM 360, GE 635, CDC 6600, and UNIVAC 1108. In the mid-1970s, major versions of MPS underwent a significant update and extension, taking on their current and likely final form, at least for large mainframes. Until the replacement of MPS, in the mid-180s, work continues and substantial improvements are made in speed, reliability, support control and data management systems and application techniques. Mini-computers emerged in the mid-1960s as smaller, more affordable alternatives to mainframes, with the Digital Equipment Corporation's DEC, PDP-8, introduced in 1965, widely considered the first true minicomputer. They offered interactive, direct user interaction and were used for scientific, engineering, and business applications, significantly expanding computer access beyond large institutions. This distinct class of computers thrived through the 1970s before declining in the 1980s and 90s as technology progressed, eventually paving the way for the personal computer. Due to the lack of commercial software for optimization on minicomputers, in 1978, Jesus Velázquez Bermúdez, in his first company, PDC Ingeniería, developed an optimization solver in Fortran, for a ModComp Classic 7870 computer. Due to computational limitations, many advanced ideas were used that will be of great use in the design of Optex GPU. At that time, the PDC primal/dual algorithm could be comparable to today's best algorithms, IBM CLEX, Gurobi and Express. The first personal computer was the Altair 8800, assembled by MITS in 1975, followed by the Kenbake 1 in 1971 and the IBM PC in 1981, which became the industry standard. These innovations made computing available to the public, transforming society, business, and communication. But their ability to solve real optimization problems is very limited. A workstation refers to the configuration of a development environment or a powerful computer system, which can be a physical or a virtual computer in the cloud, designed to run demanding applications in design, engineering, or data analysis. Today, PCs have evolved to be smaller workstations. NVIDIA, the new emperor of commercial computing. NVIDIA is a company specializing in the development of graphics processing units, GPUs, that allow researchers and programmers to develop new algorithms or adapt them for specific purposes. Jen Hasoon Huang is an American businessman. Huang graduated from Oregon State University, and then moved to California, where he graduated from Stanford University. He is the co-founder and current president and CEO of NVIDIA. As of July 2024, he is the 11th richest person in the U.S. with an estimated net worth of $118 billion. For the Da Vinci and Einsteins of our time, NVIDIA is pioneering the development of a form of accelerated computing that is loved by the world's most demanding users, scientists, designers, artists, and gamers. Driven by the insatiable demand for better 3D graphics and the sheer volume of the gaming market, NVIDIA has turned the GPU into a computational brain, at the exciting intersection of virtual reality, high-performance computing, and artificial intelligence. Now, HI is working on developing special GPU-oriented algorithms to implement the artificial brains. Below are the features of the latest GPU offered by NVIDIA. Your understanding should help develop the implementation of Optex GPU. The Central Processing Unit, CPU, is the brain of the computer, providing the instructions and processing power to do its job. To give these instructions, a CPU must be able to think quickly, so CPUs are equipped with a large amount of cache memory. The CPUs are equipped with multiple cores. These cores make use of the cache to reduce latency, allowing the CPU to process instructions provided by applications faster. This makes a CPU good at serial processing, and can simulate parallel processing, applying round-robin CPU management policies. Today, a graphic processing unit, GPU, is designed to handle work related to images, such as graphics, effects, and videos. To be effective, a GPU must be able to handle a large amount of data at the same time. The GPU must have high performance. For example, when you're gaming, you want to maximize the frame rate, FPS, to allow for a smoother gaming experience. GPUs do this by breaking down problems into thousands or sometimes millions of separate tasks and solving them at once. This is called parallel processing, and that's why GPUs are equipped with hundreds or even thousands of more specialized cores, giving GPUs the high performance they need. The image shows the architecture of the CPU and GPU. A CPU has a lot more cache compared to the GPU. This reduces the CPU's need to access slower underlying storage, such as a hard drive, and therefore reduces latency. It allows the CPU to think faster. The image also shows that a GPU consists of many more cores than a CPU, the green squares. These cores are less powerful than the cores used in a CPU, but they allow the GPU to perform similar calculations in a parallel data stream. Traditionally, optimization problems are solved by making use of the power of CPUs, ignoring the possibility of working with GPUs. However, the current power of GPUs, and the evolution of thinking around algorithm design, allows us to explore other possibilities, whose experiments have already shown that this is totally viable. Some cases reported in the literature are analyzed below. Blackwell NVIDIA, a new class of AI superchip. It is the last GPU produced by NVIDIA. Blackwell architecture GPUs pack 208 billion transistors and are manufactured using a custom-built TSMC4NP process. All Blackwell products feature two reticle limited dies connected by a 10 TB per second (TB/s) chip-to-chip interconnect in a unified single GPU. The second-generation transformer engine uses custom Blackwell Tensor Core technology combined with NVIDIA TensorRT LLM and NeMo framework innovations to accelerate inference and training for large language models, LLMs, and mixture of experts, MO, models. To supercharge inference of MO models, Blackwell Tensor Cores add new precisions, including new community-defined microscaling formats, giving high accuracy and ease of replacement for larger precisions. The Blackwell transformer engine utilizes fine-grained scaling techniques called microtensor scaling to optimize performance and accuracy, enabling 4-bit floating point (FP4) AI. This doubles the performance and size of next-generation models that memory can support while maintaining high accuracy. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, and its marketing process. The current state involves the integration of edge computing and cloud computing to implement highly complex mathematical models. For several years now, the mixture of computers and algorithms has been a fact thanks to the evolution of parallel mathematical thinking, the basis of artificial brains. Computing is evolving by leaps and bounds, which is giving rise to new visions of computing solutions, in this case based on specialized, low-cost, high-performance devices. This is the case of the Graphics Processing Unit, GPU, originally called array processors, an electronic circuit that can perform mathematical matrix calculations at high speed. And the case of the Jetson Orin Nano Super Developer Kit designed to accelerate the development of AI applications on embedded devices. It can be used for a wide range of applications, including image and video processing, robotics, IoT, and cloud-based AI, producing high-performance computing and low power consumption. This new way makes it possible to build computers composed of swarms of integrated smart devices such as GPUs, and GPUs, low-cost devices, combined with CPU clusters, allow the construction of low-cost supercomputers, which can use more elementary supercomputers than supersolvers. AI application devices. This implies that applications are deployed using intelligent devices based on the symmetrical atomization of systems and/or processes. As is the case with GPT-based artificial intelligence. This will give greater computing power to current artificial intelligence. Blackwell GB202 GPU. The full GB202 GPU includes 12 graphics processing clusters, GPCs, 96 texture processing clusters, TPCs, 192 streaming multiprocessors, SMs, and a 512-bit memory interface with 1632-bit memory controllers. The GB202 GPU also includes 384 FP64 cores, 2 per SM, which are not depicted in the above diagram. The FP64 flop rate is 1/64 the flop rate of FP32 operations. The small number of FP64 cores are included to ensure any programs with FP64 code operate correctly. Similarly, a very minimal number of FP64 tensor cores are included for program correctness. The GPC is the dominant high-level hardware block within all GB20X Blackwell family GPUs, with all the key graphics processing units residing within a GPC. Each GPC includes a dedicated raster engine, 2 raster operations, ROPs, partitions, with each partition containing 8 individual ROP units, and 8 TPCs. Each TPC includes 1 polymorph engine and 2 SMs. The NVIDIA Streaming Multiprocessor, SM, is a core component of the NVIDIA GPU architecture, playing a key role in the GPU parallel processing capabilities, enabling massive parallelism through its various cores, CUDA, Tensor, RT, efficient warp scheduling, memory management, and support for modern workloads like AI. Each full GB202 chip contains 192 SMs, and each SM includes 128 CUDA cores, 1 Blackwell 4th generation RT core, 4 Blackwell 5th generation Tensor cores, 4 texture units, a 256 kilobytes register file, and 128 kilobytes of L1/shared memory, which can be configured for different memory sizes depending on the needs of the graphics and compute workloads. Tensor cores are specialized high-performance compute cores that are tailored for the matrix multiply and accumulate math operations that are used in AI applications. They provide groundbreaking performance for the matrix computations that are critical for both deep learning, neural network training, and inference operations. Generative AI models have improved in capabilities since the first ones, released in 2022. But the improvements have often come with an increase in parameters and size. As models grow in both compute and memory requirements, it can be difficult to run such models even on the latest hardware. As a further improvement to existing ray tracing solutions, all megageometry APIs are designed to be fully batched, with their input parameters driven entirely from GPU memory. This lets the game engine run logic like modern level of detail, LOD, selection, animation, culling, and others efficiently on the GPU, while minimizing round trips to the CPU. With effective use of megageometry APIs, an application can practically eliminate CPU overhead related to bounding volume hierarchy, BVH, management. In this case, the image of the crab is handled as a finite element structure discovered by megageometry. Finite elements and differences are structures commonly used in engineering, and in many dynamical mathematical models they can be associated with the change of the decision and state variables of the system being modeled, which represents the gradient of these variables. Hi is exploring the use that can be given to megageometry for the evaluation and visualization of the results of a dynamic mathematical model. This is directly related to visualization through digital twins. Quantum computing uses specialized technology, including computer hardware and algorithms that use quantum mechanics, to solve complex problems that classical computers or supercomputers can't solve, or can't do it fast enough. Qubits are the basic unit of information in a quantum computer. Unlike classical bits, which are 0 or 1, a qubit can be in a superposition of states, 0 and 1 at the same time, which greatly increases its computational capacity. Quantum algorithms take advantage of these quantum properties to run complex calculations and find solutions to problems that are intractable by classical computers. IBM's System 2 quantum computer costs between $10 and $50 million. The high cost includes the hardware itself, specialized environments, like cryogenic systems, ongoing maintenance, technical support, and software updates. Access to cloud-based quantum computing is much cheaper, with providers offering various plans. For a while, it's the viable alternative for the industry. Although it is the state-of-the-art of computational power, it will not be discussed in this video. According to scientist Jeff Hawkins, everything indicates that the structure and joint functioning of the neocortex and hypothalamus is like the structure of the most advanced optimization algorithms. This strong relationship can serve to deepen the knowledge of the two disciplines, artificial intelligence and mathematical programming. Starting from the perceptron, the first artificial neuron created, the knowledge of neuronal modeling has evolved, currently having multiple types of artificial neural nets. The objective is to integrate the information from the artificial cortex with the communications and actions that the artificial hypothalamus must perform. The greatest advantage of mathematical artificial neurons is that they represent clearly defined objects within a system, that communicate with each other through fully known mathematical laws, and that they comply with laws with transitivity and divisibility laws, in such a way that a system can be atomized, to the level of knowledge that the scientist on duty has. This process leads to the atomization of the system, so that a problem of large dimensionality becomes a large number of problems of very low dimensionality. Hi investigates the implementation of artificial brains based on smart devices specialized in solving optimization problems. This possibility can be focused on the implementation of the simplex method, which is the central algorithm around which all the different formats are solved. Convolutional neural networks, CNN, were created to identify images that are an area of interest for NVIDIA GPUs, as much of today's artificial intelligence is concentrated in image processing. A CNN assimilates an input or output matrix to an image. This is true when you consider that images on a computer are stored in arrays of pixels. The diagram presents an example of a network geared towards image recognition of freehand numbers. In this case, the result is a discrete indicator associated with the number read. A CNN applies a set of convolutional filters, kernels, to the input images. Each filter activates different characteristics of the images, allowing a quick and effective training. CNNs can be considered totally successful for their purpose. Now, instead of images, we can have input and output matrices, from past experiences of an industrial, economic, or social process, that relate the input parameters to the output results of mathematical models used in the management of a company. An example is the methodology used to determine a transfer function for thermoelectric power plants, when an exact mathematical function that converts inputs and outputs is unknown for determine a coal blending strategy, CBS. Imitator is a CNN that transforms CBSs from the past and the possible mixture of the input carbon into dimensions compatible with the characteristics of the output carbon, allowing pre-trained models to determine the characteristics of the resulting carbon, and thus be able to optimize the process. Imitator's design is based on a combination of multi-head attention mechanisms and transposed convolution matrices that are used for feature extraction and input transformation. The result matches the common input dimensions required by pre-trained image classification models. This implies that artificial intelligence tools for pattern recognition, images in this case, can be used in engineering projects, if we look them as simple matrices. This extends to the AI included in NVIDIA GPUs. Like the fact that NVIDIA has developed tools to manage predictive artificial intelligence in GPUs, looking to the future, High believes that one of the next steps is to develop optimization-oriented intelligence, or prescriptive artificial intelligence, thinking that it is a future that is beginning to develop. The first step is to demonstrate that, in the current state of technology, GPUs are already a solution that surpasses conventional optimization. This is High's vision, supported by its experience and the research already carried out by several scientists in the area. Exterior point linear programming algorithms. In linear programming, primal and dual methods are two complementary approaches to solving the optimization problem. The primal method focuses on finding the optimal solution directly from the original formulation of the problem, while the dual method is based on solving a related transformed problem based on the theory of duality. Primal simplex method. It is the traditional method for solving linear programming problems. Start with an initial feasible solution and iteratively seek to improve it until optimal is reached. It is used when you have a feasible initial solution. Dual simplex method. It is used when there is a solution that satisfies the optimality of the objective function. It is called dual feasible, but is not feasible for the original constraints, primal unviable. It is useful when working with problems where primal feasibility is more difficult to satisfy than dual feasibility. Primal dual simplex method. It combines the advantages of both methods to improve efficiency in solving linear programming problems. It can be more efficient in certain types of problems, especially those with high dimension or degeneracy. The method uses a point that is feasible and optimal simultaneously, using iterations that improve the solution in both aspects. The paper. Efficient implementation of the simplex method on a CPU-GPU system. And the paper. Multi-GPU implementation of the simplex algorithm. Proposes its implementation through Compute Unified Device Architecture, CUDA, in a multi-GPU architecture. NVIDIA introduced CUDA in 2006, a software technology that allows users to solve many complex problems with their GPU cards. The image shows the processing times for the different sizes of LP problems, for sequential and parallel algorithms. We can see that, for each LP problem size, the dispersion of processing time is low. Although the processing time increases with the problem, the parallel algorithm, CPU-GPU, is always faster than the sequential algorithm, CPU. The table shows two indicators of the gain in speed due to the use of PIS, speed up 1 CPU versus 1 PU, and speed up 2 PU versus 2 PU. Both speed up 1 and speed up 2 increase with the size of the problems. For small size problems, for example 1000 by 1000, the speed up 1 is relatively small, average equal to 2.93 times, because the GPU power is lightly exploited. This gain can reach 12.74 times, for large instances. Speed up 2 indicates an additional gain that reaches an additional level of around 1.93, the ideal level is 2, which shows that using 2 GPUs leads to a very small loss of efficiency for large problems. The total speed 1 would be 24.5 times. This confirms the advantage of the proposed approach, as the use of multiple GPUs allows large problems to be solved efficiently, in a reasonable processing time. The multi-GPU implementation of the simplex method is realized via CUDA, Compute Unified Device Architecture of NVIDIA for GPUs. The computational results were obtained with a system with one CPU and two GPUs. The CPU was a 2.66 GHz Xeon E5640 and two NVIDIA Tesla C2050 GPUs. CUDA 3.2, Compute Unified Device Architecture of NVIDIA for GPUs, was used for the parallel code and GCC for the serial code. Computational tests were carried out on randomly generated instances for non-sparse LP problems. Displays processing times for different sizes of LP problems and for sequential, blue, and parallel algorithms red and green. Parallel algorithms, with 1 and 2 GPUs, are always faster than the sequential algorithm. In the sequential case, for issues of size 8000 by 8000 the processing time exceeds the 16-hour limit. The tests show a maximum speedup of 24.5 with two Tesla C2050 boards. This research demonstrates the effectiveness of the methodology. Julia is a high-level, general-purpose dynamic programming language. Julia is designed to be fast and productive for data science, artificial intelligence, machine learning, modeling, and simulation, and is mostly used for numerical analysis and computational science. Distinctive aspects of Julia's design include a type system with parametric polymorphism and the use of multi-send as a core programming paradigm, a default just-in-time (JIT) compiler, with support for early compilation, and an efficient, multi-threaded, garbage collection implementation. Julia does not support classes with encapsulated methods and instead relies on structures with generic methods not linked to them. Julia runs similarly to scripting languages, using their runtime, and allows interactions, but Julia programs can also be optionally sent to users in a ready-to-install execution file, which can be done quickly, without the need for pre-installed code. The commercial solver companies, such as Gurobi, try to use GPUs to speed up their solvers, but the early efforts were unsuccessful. The fundamental reason is that GPUs do not work well for solving sparse linear systems, which is the computational bottleneck of simplex or barrier method solving LP. The restarted primal dual hybrid gradient, PDHG, is a GPU implementation to solve LP. The design of CUPLP JL is illustrated in the figure. To avoid costly data transfers between the CPU and GPU, CUPLP JL runs as much as possible on the GPU and is not oriented to a spare linear array. Only two CPU-GPU communications are required for CUPLP JL. One transfers the scaled LP instance after preconditioning from the CPU to the GPU, while the other moves the final solution from the GPU to the CPU as output. The main iterations run entirely on the GPU, and there is no need to transfer any vectors before termination to alleviate expensive CPU-GPU communication. The figure shows the number of instances solved by CUPLP JL and three Gurobi methods in MIP relaxations at a given time, without using the presolve option. One observation is that the number of instances that Gurobi can resolve for a given runtime does not differ much for moderate and high accuracy. On the contrary, this difference is more evident in the case of CUPLP JL. This is a feature of a solver based on first-order methods. It should be noted that CUPLP JL has a computational overhead of around 1 second due to the GPU kernel release time. The figure shows the number of instances solved by CUPLP JL and three Gurobi methods in MIP relaxations at a given time, without using the presolve option. One observation is that the number of instances that Gurobi can resolve for a given runtime does not differ much for moderate and high accuracy. On the contrary, this difference is more evident in the case of CUPLP JL. This is a feature of a solver based on first-order methods. It should be noted that CUPLP JL has a computational overhead of around 1 second due to the GPU kernel release time. The figure shows the number of solved instances of CUPLP JL and three PDLP implementations that use different threads. As shown in both panels, CUPLP JL has significantly higher performance than all PDLP CPU versions, regardless of accuracy. Deploying multiple GPUs uses some communications to synchronize GPUs, which depend on how the problem is spread across GPUs. The process is: the constraint matrix is divided vertically to minimize communication. After preparing the problem, the CPU creates threads that will manage the GPUs. Each of them then initializes its GPU and loads a subarray into its gram. During an iteration, each CPU thread simultaneously launches the steeper edge kernel to get a local input variable. This is where the first communication comes in. Each GPU must share its local result with the others. They then narrow down the local result to choose the same optimal input variable. Because of the selected split, only the CPU thread that contains the input variable launches the expansion kernels to select the output variable. The column of this variable, called the pivot column, is required for all other GPUs to execute the pivot step. Therefore, this column, along with the output variable, is transmitted, and finally, each GPU prepares and launches the pivoting kernel without further communication. Note that GPUs communicate with each other through CPU threads. The test environment was configured as CLP, a sequential implementation of the revised simplex method, was chosen for the comparative tests between a standard solver and GPU solvers, using the netlib problem repository. CPU server, 2 Xeon X5570, 2.93 GHz, with 24 GB of DDR3 RAM, and a GPU computer system, NVIDIA Tesla S1070, connecting 4 GPUs. Each GPU has 4 GB GDDR3 graphics memory, 30 streaming multiprocessors, each holding 8 processors, 1.4 GHz. One GPU delivers a maximum throughput of 1 flops for single precision floating point, 80 flops for double precision floating point, and a memory bandwidth of 100 GB per second between threads and gram. A time limit of 1,250 seconds was imposed. As shown for large enough issues, constraints greater than 750 and variables greater than 3,750, GPU implementations substantially outperform CLP. A time limit of 1,250 seconds was imposed. However, with small issues, CLP is more efficient, which is normal due to technology overload, but CLP continuously grows and explodes when the problem size grows above 750 constraints. Implementations of the revised simplex method are strongly influenced by the density of the array. The denser the problem, the slower the CLP will run. However, to dig deeper into how these deployments behave under various densities, we measured the execution time in a fixed size problem, 500 by 2000, but with an increasing density. Finally, the GPU solver was validated by calculating the correlation between the measurements and the 1 to 4 GPU models, which was above 0.999. For very large problems, constraints greater than 5,000 and variables greater than 25,000, the predicted acceleration is almost optimal up to 40 GPUs. NVIDIA ChewOpt is a GPU-accelerated, open-source solver for decision optimization, excellent in mixed integer linear programming, MILP, linear programming, LP, and vehicle routing problems, VRP. Designed to address large-scale problems with millions of variables and constraints, ChewOpt enables near real-time optimization, resulting in significant cost savings. With a record in the mixed integer programming library, MIPLib, and 23 world records in routing benchmarks, ChewOpt delivers breakthrough performance in solving complex real-life optimization problems. Record-breaking NVIDIA ChewOpt algorithms deliver route optimization solutions 100x faster. Quantum computing and artificial intelligence are two transformative technologies that, when combined, create quantum AI. This integration leverages the unique properties of quantum mechanics, such as superposition and entanglement, to enhance AI's capabilities to solve complex problems, optimize processes, and analyze massive datasets. Quantum computing operates on qubits, which can represent multiple states simultaneously, unlike classical bits that are binary, 0 or 1. This allows quantum computers to perform calculations at exponentially faster speeds, making them ideal for AI tasks such as machine learning, optimization, and data analysis. Quantum computing, unlike classical computing, is a relatively recent development. Its origins date back to the late 1970s, when it first appeared in science fiction. It was in 1981 that Richard Feynman was credited with pioneering the concept of the quantum computer. In 1985, David Deutsch formalized the concept of a quantum computer, marking an important milestone in the field of quantum computing. Theory of quantum mechanics: it is the law of the smallest things at the scale of atoms and electrons in subatomic particles that causes an atom to overlap and become a state of having a combination of 0 and 1, it keeps changing. Superposition is the fundamental principle of quantum computing. It allows more than one bit to take on a single state, makes the operation of quantum computers faster, there will be two states at once, and much more information can be stored at the same time. Qubits are represented by a superposition of several possible states. A qubit uses the superposition phenomena of quantum mechanics to achieve a linear combination of two states. A qubit can represent a 0, a 1, or any ratio of 0 and 1 in the superposition of both states, with a given probability of being a 0 and a given probability of being a 1. The amount of information that a qubit system can represent increases exponentially. The information that 500 qubits can easily represent would not be possible even with more than 2 to the classical 500 bits. A classical computer to find the prime factors of a 2048-bit number takes millions of years. With qubits, this calculation could be done in a few minutes. Interference is a key idea in quantum computing. It is to control the probability of a system of qubits collapsing in measurement states. It is a byproduct of superposition. It is what allows us to skew the measurement of a qubit towards a desired state, or a set of states. Entanglement is like two objects connected in one way or another, that by knowing one of them, we can have a clear idea of the other, without having to measure it. In quantum computing, the probability of one qubit state can be affected by the change in the probability of another qubit state. This phenomenon is called entanglement, which is created through quantum gates by performing specific operations on the qubits that result in inseparable states of qubits. Quantum entanglement occurs when two or more particles are correlated, so that the state of one qubit depends on the state of another qubit, regardless of the distance between them. If the state of one qubit changes in the entangled system, the states of all other qubits will be affected. Just as a binary bit is the basic unit of information in classical computing, a qubit, or quantum bit, is the basic unit of information in quantum computing. The image shows how two qubits are in non-entangled, left, or entangled, right, quantum states. Quantum noise has several manifestations in quantum systems, and can affect various aspects of quantum computing. Some common examples of quantum noise include measurement noise. The act of measurement can cause a quantum system to lose superposition and collapse into one of its states, introducing uncertainty into the result, due to the probabilistic nature of the measurement process. Decoherence. Interactions with the environment can cause quantum systems to lose quantum superposition, entanglement, and interference, affecting the performance of algorithms. Quantum noise poses a major challenge for quantum computer science. To address this challenge, researchers have been working on quantum error correction techniques, which are essential for preserving quantum states against the detrimental effects of measurement noise and decoherence. The quantum approximate optimization algorithm, QAOA, is a variational quantum algorithm that aims to solve combinatorial optimization problems that are classically intractable. The variational quantum eigensolver, VQE, method is a similar quantum approximation algorithm developed independently of QAOA. In essence, both algorithms aim to find a ground state of a Hamiltonian with a slightly different approach. Using a quantum solver, such as QAOA or VQE, we can solve a mathematical model to obtain the optimal values for the decision variables, while satisfying the constraints of the problem, optimizing the target function. Several researchers have tried to find variations that produce better performance for QAOA and/or VQE, than there are many options for quantum optimization algorithms. The paper, Quantum Computing for Production Planning, presents a case of a QAOA application. This research investigates the potential of quantum computing in production planning, and addresses the limitations of conventional computing approaches, which have been partially effective, trying to solve complex optimization problems, accurately predict demand, and manage supply chains efficiently. The capabilities of quantum computing offer promising solutions to overcome these obstacles and revolutionize production planning processes. The mathematical formulation represents a model of production planning with the aim of minimizing production costs and meeting demand and resource constraints. Decision variables determine the selection of tasks and the number of resources assigned to each task in different periods. The target function minimizes the total cost of production, and constraints ensure that demand is met, resource capacity is not exceeded, and production times are respected. Algorithm implementing production planning problem based on the provided mathematical formulation. Using an optimization solver, such as CAOA or VQE, we can solve this mathematical model to obtain the optimal values for task selection and resource allocation variables, which will minimize the total production cost while satisfying the demand and resource constraints. This study investigates the power of quantum computing in a specific field of application, production planning. It demonstrates the ability to solve real problems and its ability to overcome the limitations of conventional computer methods, which face serious difficulties when problems are combinatorial. This research seeks to bridge the gap between quantum computing and the field of engineering optimization by evaluating the potential benefits, limitations, and pitfalls associated with employing quantum computing. Chaining optext to the quantum algorithm. HI's approach to quantum AI is based on two steps. The formulation of the models is based on optext, optimization expert system, which generates the programs without the need to perform programmer activities. The algorithm already coded for execution is sent to the quantum computer. The evolution of optimization has brought with it the evolution of the products offered, which were originally limited to simple mathematical models. Modern technology companies now offer new products that originate from the power developed in methodologies, computational technologies, and algorithms. For example, the products offered by HI are Artificial Business Management, ABM, aimed at the management of companies under the supervision of artificial intelligence. Business Artificial Brains, AB, construction of artificial brains for companies, are the architecture of the management systems. Enterprise-wide optimization systems, EWOS, IT systems in which management systems are implemented, and high-complexity mathematical models, HCMM, are the different engines that drive an ABM. They are stored in the EWOS. Optimization, like everything in recent times, will evolve from systems that operate in a discrete and sequential way, manually guided by humans, to autonomous systems that operate in real time, based on parallel mathematics. Through artificial intelligence, modern optimization can solve an executive's question: how much should I produce from a SKU, in each location, in each period, and how should I transport it to markets? This is a new approach to artificial intelligence, as this question cannot be solved with GPT models. However, HI's entrepreneurial brains can simultaneously solve all questions, in real time, at any time, by taking a holistic view of the company. In January 2025, Informs, the world's largest association for professionals and students in operations research, or artificial intelligence, analytics, and data science, selected the 6 finalists for the prestigious 2025 Franz Edelman Award for Achievement in Advanced Analytics, Operations Research, and Management Science. Recognized as the pinnacle of achievement in the application of analytics and operations research, the award, often referred to as the OR Nobel Prize, celebrates breakthrough research and innovations that are transforming industries, improving lives, and shaping a smarter, more sustainable future. The winner, USA Cycling. Project 405 was a data-driven initiative that improved USA Cycling's women's team pursuit strategy for the Paris 2024 Olympic Games. The project focused on key factors such as rider power, aerodynamics and team coordination to create the perfect race plan, aiming for a time under 4 minutes and 5 seconds. By analyzing performance data and using advanced technology, the team identified the best riders and strategies. This approach helped them go from 8th place at the World Championships to Olympic gold a year later, showing how data and smart planning can lead to huge improvements in sports performance. Other finalists. Amazon. By 2021, Amazon was shipping billions of packages each year through its large network of warehouses in the US. However, as the company grew, it faced rising costs and challenges in delivering items quickly. To solve this, Amazon assembled a team of operations research and supply chain experts who used network optimization, machine learning, and simulation to create a new strategy called regionalization. In 2023, this strategy helped reduce cost to serve by 45 cents per item in the U.S., and helped Amazon achieve its fastest delivery speeds ever globally, improving both efficiency and customer satisfaction. Lufthansa Group. In 2019, Lufthansa Group began work to improve the way airlines handle disruptions such as flight delays using advanced operations investigation techniques. In partnership with Google Research, they developed new methods to optimize aircraft, passenger and crew scheduling, ensuring smooth recovery when problems arise. This system is used by Lufthansa's subsidiary, Swiss International Airlines, saving €12 million and reducing CO2 emissions by 14,000 tons. The system is being rolled out to other Lufthansa Group airlines, with plans to generate multi-billion-dollar savings and reduce up to 50,000 tons of CO2 each year. Flipkart. It is one of India's leading e-commerce marketplaces, delivering millions of orders a day. In recent years, Flipkart has developed an advanced supply chain planning platform that has substantially increased the level of intelligence in demand estimation, inventory management for vendors, and network and capacity planning. Based on data science and operations research methods, this platform has significantly improved operational planning for Flipkart and sellers and has thus enabled both Flipkart and sellers to grow rapidly while significantly reducing operational costs and improving the customer experience. SF Express. SF Express is Asia's largest integrated logistics service provider, ranking 4th globally. Since 2018, a team of experts has been optimizing its integrated network using advanced operations investigation techniques. These strategies help SF Express improve its operational and strategic decisions, including planning Asia's first cargo-focused air hub. Since its inception, the project has reduced service times for more than 1 billion packages, saved the company more than $1 billion, and reduced carbon emissions by millions of tons. This success shows how smart planning can generate substantial benefits, improve the customer experience, and help protect the environment. WM is the new brand of waste management, a leading North American provider of comprehensive waste and environmental services, which officially rebranded in 2022. After the pandemic, WM struggled to optimize industrial waste collection routes due to unpredictable conditions and customer needs. Manual route creation was inefficient with too many factors to consider. To address these challenges, WM developed and implemented dynamic route optimization. Using advanced analytics and operations research, the company now automatically builds efficient routes while improving safety and customer service. With this first-of-its-kind technology suite, WM's industrial business achieved a 50% reduction in airstrike safety incidents and unprecedented increases in efficiency and profitability. If you want your company to be at the level of the state-of-the-art of Industry 4.0, you need to rationalize that mathematics, and more specifically optimization and artificial intelligence, are a mandatory part of the path. It is a requirement to be a winner. As George Bernard Shaw would say, imagination is the beginning of creation. You imagine what you desire, you will what you imagine, and at last you create what you will. Thank you very much for your attention.